you for the introduction and the HPC Advisory Council to inviting me to do this talk, and also for the organization of this event in the beautiful city of Valencia. I would like to talk about a tool that we started to develop about 1 year ago, and with the aim to identify some efficiency issues in the job executions in an HPC system. So, okay, I will talk about the motivation of this tool, of why we started to develop this tool, how we architect the solution, and some final conclusions. But let me first talk about the company, who is HPCNow. We are a global HPC consulting company. We have a background in both in IT and scientific, because we have in the team we have people coming from the computing science field and from the engineering field. We don't sell hardware, we only provide HPC services and solutions on top of this hardware. And I think that what better describes our company is that this topic, we are a user-oriented company, precisely because we have this experience for several members of our team in several national supercomputing facilities. This is the centers and the institutions where we have been working on. You can see that there are several big supercomputing facilities. Okay. So this is what we do, basically. It's a very small summary. Starting from the initial part of a procurement of a new HPC facility, we can do the consulting service. Well, I don't want to bother you with all the details, but what we could provide is because we are hardware and software agnostics, we can provide competitive costs for best performance solutions. Once you have your hardware in your premises, we can do the installation. And at the end of the day, what we can provide is a complete setup of the HPC system and a ready-to-use installation. Once you have your hardware installed, we can provide you administration of the solution. We can do it local or remotely, and we can set up some proactive alerts to monitor the hardware and the services. We can also design the backup solution, security. Well, I think we could pass along these slides about the support. We can do technical support both for sysadmins, are also for the scientific users, because we have people in the team which has been involved in several research institutions. And finally, we can do the training here both again for system and users. And at the end of the day, what we want is that the system that we install has a good, the better possible usage. So we try to provide sysadmins with a complete documentation with all the configuration and setup of the cluster. This is some of the software tools that we have a lot of experience on installing, and configuring, and we can provide also support and training for that, starting from batch schedulers like Slurm or LSF, monitoring tools, Ganglia or Grafana. There are cluster management tools, as now is our solution, but we have also accreditations from Bright Computing. Parallel file system, we could provide first and second level support for BGFS. But we have installed also PF systems, or CPFS, or even HDFS for big data and Hadoop solutions. Regarding user environment, modules, LMOD or EasyBuild to easily install software stack in a cluster. Several development tools, compilers, debuggers, and profilers. And for scientific and engineering applications, there is a big list of them. So, but we can also provide this support for example, Gaussian BASP or whatever, or another engineering software, Fluent or Abacus. On the virtualization world, we have installed several frameworks, for example, OpenNebula or OpenStack, containers with Docker or Singularity, and HPC portals. Well, you can see there are lot of different tools for do that. We have been involved in the open source community and did some contributions for some projects, for example, EasyBuild or Singularity or Open HPC. And we have also been involved in with Praise and other European projects. Well, this is more or less the picture of what HPCNow is. This is our use cases. We have customers in the public sector, or we have been involved with several institutions like Barcelona Supercomputing Center or CESGA, which are the big HPC facilities in Spain, or the IPC in the Basque Country. But also we have big key projects in private companies like pharmaceutical, Pfizer, or automation, so in IDEADA, or some startup companies in the bio field, for example, Made of Genes or NBD, which we can help them to get their services and their hardware. We did the maintenance of their services. For example, now we have just installed in the King Abdullah University of Science and Technology what I think it will be the biggest BGFS nowadays, and it's expected to be in the third position in the IO 500 list. So, well, you can see there is lot of institutions here, and our team is only 10 people. So sometimes people ask us, how do you manage to deliver on-time projects to such an amount of institution? I think there are three more or less keys to do that. One of them is the expertise, the experience that we have gathered by working with the national HPC facilities that we are been working. The second key is about some reputation that we have gathered also in the open source community by being involved in several projects. But the key point, I think, it's automation. We have to try to automatize every single process that we have, every single tool that we need. And this, in fact, this is what it's all about. And in fact, this is what this tool that I will present is about. Because we, as a computational scientist, we need to, or we want to have the better performance that we can of a job. And we want to get an in-depth analysis of what is a job is not performing as we expected. And we didn't find any tool in the market that do that, so we started to develop this new tool. Okay, so I will enter more in detail in the motivation of the tool, and why we want to get this. Why we want to identify these opportunities to improve the efficiency in the HPC cluster. Well, when you procure a new cluster, what you expect is to have it working at the very next day, working 100% of its capacity, with no delays, with no waiting queues for the user, and get in this configuration until the end of life of the cluster. Of course, this is very far from the reality, and you have to take into account that you have to accommodate the workload that you will have in, I don't know, 3, 5, 6 years from now on. So what we see from our experience is that at the end, what you have is a cluster that it's a bit underutilized in the very beginning of its life, but presenting some cluster contention at the end of the life. So at some point in the life of the cluster, you will start to face some cluster contention, some problems with the hardware that is no longer support. You will find, and we are finding now, that there appear some workflows that are very high demand in I/O, because we are using more data than before. So all of these problems are conducting to a higher waiting time for the users, and maybe the risk of the user dissatisfaction in the cluster, in the use of the cluster. So what potential solutions are for this? You can buy a new cluster, for sure. You can always do that, but you know that it's a procurement of a new cluster. It's a large process, and maybe there are some complex RFPs to get this new cluster. A second possible solution is to use the cloud, use cloud bursting, and if if your workflow follows more or less this kind of pattern in which you have some deadlines in your projects and you need some extension of your capacity in some specific points of time, then cloud bursting is your solution for sure. But at the end, what you have is that the two first solutions need a lot of investment. The first one, you have to pay everything up front. The second solution, you need to pay as you go. But there is another solution, which is what we are talking about today, and it's improving the efficiency of your jobs. Because by improving the performance or the efficiency, you are somehow creating this more allocation for new jobs, and you need no invest in hardware capacity. For sure, you will have to invest in hiring talented people to do that, but no in hardware capacity. So here, a short example, if you have running a job with a full configuration, and this is the timeline, and you are not, you have done any optimization of that, your job will finish at this time. But if you are able to identify possible optimizations of this run, in the case you can act on this, doing some optimization on the application or whatever. This is not interesting for us just now. The interesting thing is that you could get a performance win in the percentage that you can achieve, and you are getting more efficiency in this cluster. At the end of the day, what you have is more resources to allocate new jobs. So, how you can identify these joining opportunities easily? This is the key question. Well, traditional tools like Ganglia, they are not capable of representing what we need. So there is no link to user, there is no link to job, no link to other nodes that maybe are allocated slots for this very same job. So we cannot gather information of the efficiency of in a job-based pattern. So what we developed is this new tool, which has 3 key points. What we have is to review resources requested versus used. So we can see in which jobs we could act. We do it in real time monitoring. That allows us to the possibility to trigger real-time actions. I mean, kill this job because it's a waste of time. And we are doing nowadays in a 30 seconds resolution. So we are gathering metrics in every 30 seconds, which is quite reasonable for the majority of HPC workloads. The architecture of the solution, we are using Elasticsearch. We are dealing with a lot of jobs, we are dealing with a lot of nodes, so traditional databases are not enough to gather all this information. And we are using Elasticsearch for storing the data, and Grafana and Kibana represent and analyze this data. This is the traditional stack pipeline of solution for storing syslogs, for example. You have the remote syslog server. You inject the data to a Logstash instance where you filter the data and process the data and send it to the Elasticsearch destination. And so you have data visualizations with Kibana and Grafana. What we did here is just get rid of the Logstash instance because this is injecting more data that is not useful for us. We replace the data source with a custom code developed by us and inject directly the output of this code to the Elasticsearch. This is the configuration that we have on pre-production and production in some places, but we developed also a prototype that it's the difference with the old one is that we wanted to collect more metrics and do it in a lower resolution time to try to collect also data for very short jobs that extend more than 30 seconds. So we can only study, not only, we can also study jobs for high throughput computing, for example, very short jobs. And in this prototype, what we are using is a custom collect daemon, and there's a lot of Elasticsearch plugin that has been developed in the Barcelona Supercomputing Center and injecting the data to the Elasticsearch. So in the first version of the tool, we were using, this is a simple test with 380 nodes, the resolution 30 seconds. We collect 8 metrics for every job, every user. And by replacing the standard configuration with the custom configuration, we are able to lower the average size per package that we collect from 2,000 to 400. So it's with this new custom configuration, you can get a lower size in your cluster to collect to store the data in the Elasticsearch. In the prototype, as I said, we wanted to collect more metrics, and we expanded to this lot of metrics from 8 to 300, lower the resolution to 10 seconds. Of course, by doing that, the average size for the package is increased, and you can expect to waste 8 terabytes of data in a year inside the Elasticsearch. And with this configuration, with this theoretical limit, you could convert it in the number of nodes that you could study or collect data from. So with this configuration, you could have a cluster with 15,000 nodes and collect data for this cluster. This prototype, we expect to collect a lot of metrics. In bold, you have the metrics that are already implemented, and this is other metrics that we want to implement. For example, in HPC, you can maybe get some insights if your job, if your application is using the vectorized instructions or not, and act and react on that, or MPI stats and collectives, for example, among others. If you ever want or need to scale up this solution, we have done the tests in a 1 gigabyte Ethernet. You can migrate to a 10 gigabyte, so you could increase the number of events ingested. Use buffers, so you can also increase the number of events with this technique, and also add more elastic search nodes that in principle gives you the possibility to do unlimited scalability. The very interesting thing is that having this solution on production in a cluster, we see no performance penalty at all based on HPL results. So you can put this solution in your cluster. It's not disturbing your production and running jobs. This is, I don't know if you can see it here from the last end, but this is a Grafana view of the tool. Here, for example, in green, you can see the number of CPUs used during a period of 1 week. Green is CPU used. In red is the CPU that is asked for. So users are asking for this amount of CPU, but they are really using this small amount. You can see the waste of CPU cycles here. From this used CPU, here we can collect the average CPU efficiency. So in average, it's about 72%. It's not too bad, but it's not too good. I think we could add on that and try to increase the efficiency. And here we present also for a week a picture of the total CPUs underused by all the users in the cluster. We try to anonymize the names of this user, for example, because he's in average, so let's see that, he's underusing 626 CPUs on average on a period of 1 week. If we aggregate the data from the week, what we see here is that this user here in green have wasted 12 years of computational, of core hours. 12 years in 1 week. This is, we need to act upon this user and try to help him and improve the efficiency of what he's doing. The most relevant case studies, I don't know how many time I have. I mean, we have many relevant case studies. For example, for a VASP user, by improving the efficiency from 74% to 97%. This is the CPU time hours once the code was optimized. This is one case of one user using our code, in which the runnings were finishing, but not properly, and some zombie tasks were running the background, and for sure generate some problems, and we could help him in solve this problem. Well, I think it's not okay to say. And about some conclusions, is thanks to this monitoring of the job efficiency, we have been able to improve the performance, in some cases the scalability, and for sure the efficiency of the clusters. And as a side effect of that, and also we were able to detect some user mistakes early in real time, so we can act when the problem is executing, and you don't have to wait for the user to complain about the runs in your cluster are not working properly, and you have to debug and profile the application, which is a very tedious task sometimes. We avoid massive waste of CPU time, improve user workflows, and accelerate research. And the most important for me as a computational scientist is that we could improve the user satisfaction. This is a very important topic for us. So this is more or less all I have to say. I don't know if I expanded more time, or if you have any question, please feel free to shout.
Yeah. In the beginning, you said that you support also various container technologies. How deep is your support there, and are you interested in working together with, say, Docker to foster and fertilize the container usage?
Okay, well, we have no formal partnership with Docker, for example. So the support, but I cannot say that we provide first level or second level support, because we have no partnership with this
Not yet.
institution. Not yet. This is why. So, what was the question? Sorry.
I assume you use Docker Swarm for the monitoring stacks and the stack many auxiliary services that you presented here?
Yeah.
Or do you also support like HPC or AI use cases?
Yeah, we support also HPC. We are starting to use. To be honest, I have more experience with Docker than with Singularity, but for the it's not for you being here, but we are starting to use some Singularity containers for the HPC. Yeah, I think it's not a good. I like Docker because it's the tool that I use more. Starting to try to. And in fact, for this configuration, we use Docker. But the prototype is based in LXC. But yeah, we use it for this tool, but also we can provide support for other HPC users.
Do you have any tools that are working in real time or just offline after?
Sorry?
Any tools that are working on real time to see what's happening in real time in the system and then try to change things that are on the fly and not kind of getting the information and then trying to optimize for future runs?
Well, we are not aware of any tool that can do that in this per job basis that we want to get. So you can get that as a real-time solution, because if we could afford this 10-second gathering metrics, it's more or less a real-time for the HPC workflows that we have, a real-time tool. And you can define some triggers and actions in the Grafana tool, for example, in which you can say, hey, if this job is not behaving, if it's wasting more of half of the time in doing nothing, you can kill this process or not kill, but stop it, and you could restart it or whatever. I don't know if that answers your question. Okay, more questions? Okay, then. Thanks for